seminars format, I'll plan the talk in two parts. And the first part will be about this classification problem that was mentioned in the abstract that we attack using Bivariant algebraic theory. And in the second part, I will talk about Bivariant algebraic theory and how we use it to tackle this problem. But the first part, I will mention what the problem is and what our results on the problem are. So, we take an associative ring, R, right? So it's not 0 and it has a 1. And I write associative to emphasize that it will not be commutative in general, right? So recall that R is simple if it has no proper ideals, no proper two-sided ideals. In terms of elements, this means that for every non-zero element, there exists an n, an element say 1an, b1, bn, such that the sum from 1 to n of ai x bi is 1. Okay, so that's, it's equivalent to saying that every non-zero element, the two-sided ideal it generates is the whole thing, and that means this. Okay, now we call R simple purely infinite or SPI if R is not a division ring and for every non-zero x, for every non-zero x, there exists A and B, so that AXB is 1. Okay? So I recall the definition of simplicity so that you can see that purely infinite simplicity is a much stronger condition, right? You require the same thing, but in one just one shot, one summand. Okay, so purely infinite simple rings have a special behavior with respect to their k-zeros, and this is the next thing I want to say. So there's a theorem due to Ara, Goodell, and Pardo, published in 2002, that says that if R is SPI and P and Q are non-zero finitely generated projective R modules, then there exists an M non-zero so that Q is isomorphic to Q plus M. Okay? So if you look at the non-zero projective modules, finitely generated projectives, then you can subtract one from the other without leaving the realm of the non-zero finitely generated projective modules. Right? The difference of two of them is another one of them. So some observations here is that, in particular, if you put P equal to R, you get that any I wanted an M here. That any finitely generated projective module is isomorphic to a direct summand, to a proper direct summand of R. And in particular, this happens with R. Right? So this module N, which is a non-zero module, acts like zero. So a way of saying this is as follows. So say, since every module is a finitely generated projective module, it's a direct summand of R, when you look at K0, you just need to worry about those modules, those projective modules, the direct summands of R. And these are given by idempotents. So say you have E and F idempotents, then you declare that E and F are equivalent if, here should be an F, if the right ideals they generate, you can do it on the left, I do it on the right. If the left ideals they generate, which are finitely generated projective modules, which live inside R, are isomorphic, okay? And then you take V1 of R to be the idempotents of R, modulo this relation. And a corollary of the theorem above is that K0 of R is isomorphic to V1 of R minus 0. So the idempotent 0, if it is equivalent to F, then F is also 0. Right? So the class, the equivalence class of 0 consists only of 0. So I remove that class, and the result is an abelian group. And it's actually the group completion of the abelian monoid of finitely generated projective modules over R. Right? So this is an important, nice property that this class of rings has. And I am interested not in all purely infinite simple rings, but on those coming from graph algebras over a fixed field. So let me tell you a bit about graphs.
So sorry. So there's a question. Maybe you're about to explain this, but what is a good example?
What's a good example of? Well, a short. Okay, so you take vector space of countably infinite dimension over a field. Take its ring of endomorphisms. Right there is, to say the ideal, which is the finite rank operators. Mod out by this, that's purely infinite simple. Right? Or if you want a simpler version of this, the Karoubi suspension of a field is purely infinite simple.
Sorry, so the first one is what's also sometimes called a Alkane Algebra, is that right?
Well, the Alkane Algebra is a C-star algebra version of that. Oh. Yeah, you need completions and such things. So this is a pure algebra, is the Alkane Algebra. But the examples I am interested in are smaller than those I just mentioned. So what is a graph in this lecture? So what I call a graph is what other people call a quiver. So it's a directed graph. Yeah, and so what is that? So it consists of two sets related by two maps. The first set is the set of edges. The second is the set of vertices. And these are the range and source maps. So you should think of a graph as a small category minus the composition law. It doesn't have a composition law, but it has arrows and objects. And given an arrow, you know where it starts and where it ends. So you think of an edge as an arrow going from its source to its range. And today, I mean, one can consider graphs of arbitrary cardinality, but today I will only consider graphs which are finite. So it means that both the set of edges and the set of vertices are finite. Right. And yeah, and I will insist also that my graphs won't have any sinks. That means a sink is a vertex that emits no arrow. So I will insist that every vertex emits an arrow. And that means that the inverse image of every vertex, which consists of the arrows coming out of that vertex, is non-empty for every vertex. Okay.
So sorry, there's another question or comment. Is it also correct that there are no identities in this? So there's no no edges which are like a loop?
No. There are no identities. Yeah, because this doesn't have a section. Yeah, yeah, that's right. Yeah, that's right. Okay. Yeah. But I'm a non-unital person, so I even consider categories without the unit, but that's not something you mention in polite society. Okay. So if you have you have one of these graphs, and then you can write a matrix which is called the incidence matrix, whose coefficients are natural numbers that can be zero. Right? So just to avoid the discussion of whether natural numbers contain the zero or not, I put the zero there. So these are non-negative integers, and it's indexed by the vertices. So to describe it, I need to tell you what the entry is at a given pair of edges, of vertices. And that's precisely the number of all the edges that go from B to W. Okay. So now say you have a field and I'm sorry, but my field is called L. Okay, and then given a field and a graph, you get the Leavitt algebra of the graph, which depends on little l, on the field. Okay? I will not tell you, this is an algebra given by generators and relations. It has one generator for every vertex and one generator for every edge, modulo certain relations. I will give you an example later on. Okay? Fine. And this is a star algebra. So if the field, say the field comes with involution, which may be the trivial involution, the identity, then you can equip this algebra with an involution too, in such a way that when you restrict it to the field, you get the involution the field came with. Okay. So there is a particular case, I don't know if, yeah, you should be able to see there. When your field is the complex numbers. Then, and by the complex numbers, I mean the complex numbers equipped with complex conjugation. So that's my involution. Okay, so this comes with an involution, and using that involution, you can equip this algebra with a norm, and then take the closure, and this is a C-star algebra. The C-star algebra of the graph. Right. This is called the, I don't have room in the whiteboard to write it, but it's the Kunz-Krieger C-star algebra of the graph. Okay. And so here are some facts. The Leibniz passage of the graph E is simply purely infinite if and only if the C-star algebra of E is simply purely infinite. And this is because, and here I don't mean just the Leibniz passage algebra over the complex numbers. I mean over any field. So what happens is that LE being SPI for LE is equivalent to a condition on the graph, a graph theoretic condition. This is also equivalent to a graph theoretic condition and to the same condition. And that condition, which is a condition that is, say, is highly connected graph with loop, with at least one loop, is what I will call, which I won't tell you what it is what I will call that E is SPI. Okay? So there is a graph condition. I will give you an example in a moment. Okay, so I will call, there is a, believe me that there is a graph theoretic condition that characterizes both, is equivalent to both the C-star algebra being SPI and the Leibniz passage algebra over any field being SPI. Okay, so this is one fact. And the second fact is that is the following. So say, I mentioned the incidence matrix before. It was a square matrix indexed by the vertices of the graph. So I take the identity matrix minus the transpose of the inverse matrix, of the incidence matrix. This is still a matrix, which now lives in C E0 times C0. And what happens is that K0 of the C-star algebra of E is the same as K0 of the Leibniz passage algebra of E over any field. And this is just the co-kernel of the matrix ME. Okay, so the co-kernel of this matrix, which depends only on the graph, is the K0 of the Leibniz passage algebra or of the C-star algebra over any field. And well, here, since this is the K0 of a ring with unit, there will be the class of the unit, the idempotent one, or if you want, the class of the rank 1 free module. And that will be the class of the sum of all vertices. Okay, you take the sum of all vertices. So this makes sense because each vertex is a basis element of this of this free abelian group. Of this free abelian group of 0 to the 0. Yeah. And so the co-kernel is C to D0 modulo relations, and that's an element there, the class of the element there. Okay, so here is a theorem which pieces together results obtained at various times by Kunz and Krieger in 1980, Franks in 84, and Roerdam in 95, which says that if E and F are simple purely infinite, and C from coker ME to coker MF is an isomorphism, then the sister algebras of E and F are Morita equivalent. Okay? And if, moreover, 1 goes to 1, then they are isomorphic. Isomorphic in a way that preserves involution. Isomorphic as sister algebras. Okay, and so the problem is, what about LE and LF? So here, all this data, ME, MF, and the 1 depend only on the graphs, right? So given this group isomorphism between these two groups that depend on the graph, you get the Morita equivalence, and if it sends 1 to 1, you get an isomorphism. So can you get the same result with LE and LF? That's the so-called classification question for purely infinite simple Leavitt path algebras. And that's the problem I want to address. So what is known about the problem in this generality? So theorem of Abrams, Lowley, Pardo, and Smith, 2011. Okay, so if you have E and F SPI and C from coker ME to coker MF, and the sign of the determinant of ME is the same as the sign of the determinant of MF, if you have the two conditions, then LE and LF are Morita equivalent. Okay, so here under the same conditions, but with the addition of the sign, you get a Morita equivalence. So let me tell you a bit about the sign. When you have the co-kernel, you have a matrix with integer coefficients, and you have two matrices with integer coefficients, and you take their co-kernels. The fact that they are isomorphic already implies that the absolute values, let's see, this is not working. Let me try this one. Okay, that the modules of their absolute values, the absolute values, are the same. Okay, just because the cokernels are isomorphic, their absolute values are the same. This follows, this is straightforward from the so-called Smith's normal form. Okay, and then if you additionally know that the signs are the same, then you get Morita equivalence. In fact, putting together Kunz-Krieger and Frank's results, you got a similar condition, a similar theorem for C-star algebras. So it was Rotterdam using ideas of Kunz who proved that the sign didn't matter. And so he used ideas of Kunz and Kasparov's bivariant K-theory for C-star algebras. So what we do is we use bivariant algebraic K-theory. Okay.
Sorry, if I could just ask a quick question, just clarification. Yes. So in the theorem on top, this is true over any field.
Yeah. It doesn't depend on the field.
Whereas on the bottom, it's over the complex numbers.
Yeah. C-star algebras are to me, a C-star algebra is by definition over the complex numbers. Yes.
Thanks.
It could be over the reals, but I'm not considering that. Yeah. Okay. So before proceeding and explaining what the results are, let me give you the promised example. And hope that all the box of whiteboard markers that I bought starts working. So here is an example. We take Rn, let's see, Rn consists of one vertex and n loops. Okay, one vertex and n loops. Yeah, in this case, the Leavitt path algebra is called Ln, and what is this? So this is let me erase this. This is L of is a free algebra on 2n generators. Modulo some relations, which I will now tell you what they are. So I will write the relations in matricial form. So there are 2n variables. The first ones are labeled x1 to xn, and the second ones x1 star to xn star. The star is there so that you think that there will be an involution that will send xi to xi star. Okay, and yeah, so look at the row matrix X. By this I mean the row matrix whose coefficients are x1 up to xn, and the column matrix X star, whose coefficients are x1 star down to xn star. This product is to be 1. And the other product is 1, but the n by n 1. So this is the identity, the n by n identity matrix. So this is the Leavitt path algebra of this graph. Okay, so some remarks here. So what is the matrix ARN? It has one vertex and n loops. So there are n edges from the vertex to itself. So this matrix is a 1 by 1 matrix containing n there. So MRN is 1 minus n. Okay, and what is L1? So you have one variable, a single variable x times x star is 1, and x star times x is 1. That is the Laurent polynomials. And if n is at least 2, then Ln is simple, purely infinite, and this was proved by Leavitt in 1965. So an observation is that, remember that K0 of the Leavitt path algebra always was the co-kernel of the M matrix. So the co-kernel of the N matrix, in this case, is Z mod n minus 1, Z. So for example, the class of the rank 1 free module equals n times the same thing. And this is exactly what these relations tell me. They tell me that the rank 1 and the rank n free module are isomorphic. And it's the universal algebra with those properties. Okay. So I said that by these results of Abrams and co-authors, the whole point it was to distinguish, was to see whether you can distinguish between an algebra so that the algebra of a graph, so that the determinant has a plus sign or that it has a minus sign. And there is a systematic way to study it, which is called the Kunz splice. What it does is it keeps the same K0, the same co-kernel of the M matrix M, but changes the sign of the determinant. So in this particular case, this is your graph Rn, and then you add a picture like this. You add an edge in this direction, an edge in this direction, a loop here, edge, loop.
So sorry. So yes. I think many people, including me, are having trouble with the resolution. The resolution of the board got a lot worse. I think it's actually improved now.
Well, it comes and goes because of the instability of the internet connection, I suppose. Mm-hmm. But if it helps, I can shut down the curtain and turn on the electric light. Don't know if that will change anything, but I can try it if you want.
Is that better? Do people think that's clearer? I don't know if it makes a huge difference. I think it's mostly, I think it's fine now. Yeah, thanks.
Okay. So you add these edges, and then you get a new graph, so that the Leavitt path algebra is Ln minus. And so now the co-kernel of this matrix is still Cn minus 1c, but the determinant has changed. The determinant of the M matrix is now, before it was 1 minus n, and now it's n minus 1. Okay? So a particular problem that in fact you can reduce it to this, and to this for n equal to 2, that whether this algebra and this algebra and the algebra corresponding to this graph are isomorphic or not, or whether they are Morita equivalent. The class n equal 2 is special because here, if n is 2, here you get -1. So the co-kernel is 0, and the same here. You get C mod C. Okay. Now, one couple of things to notice here are as follows. This algebra, the algebra Ln, is graded with by the integers. In fact, if you I need to erase a bit here. If you take the degree of xi to be 1 and the degree of xi star to be -1, then this is graded. These relations are homogeneous with respect to that grading, so you get a C grading. Okay, so let me erase, if I may. So, and in general, LE is C graded, and now I'm talking for any E. In such a way that if omega is homogeneous, then the degree of the involution applied to it is minus the degree of omega. Okay? As it happens here. So you may think of LE, you may give it the even odd grading, and it's now C mod 2C grading. And this condition means that the involution preserves this decomposition. So if you have A0 equal to, you have A equal to A0 plus A1, with A0 here and A1 here, when you take A star, this is of course A0 star plus A1 star, and A0 star is still here and A1 star is still here. Okay, now define A bar, define a new involution by sticking a -1 in here. Okay? Same thing, but with a -1. Okay. So the resulting algebra I will call LE bar. This is LE with a bar involution. Okay. So one thing I want to mention, to make you notice, is that if you have a homomorphism, that a star homomorphism for the usual star that preserves the C mod 2 grading, then it automatically is also commutes with the bar involution. Because if it, no, if phi A star equal phi of A star and C mod 2C homogeneous, implies that phi of A bar is phi of A bar. This is an A. Okay, so yeah, this is the standard involution. The involution that when the field is C gives you, and you complete, it corresponds to the adjoint operator. And this is this new signed involution. And if you have a morphism that preserves the good involution and is C mod 2C homogeneous, then it also preserves the other involution. Okay, so here are our results, and I state them and stop. I need one more piece of notation. So for every algebra B, I write iota for the upper left-hand corner inclusion in the 2x2 matrices. And if I have two homomorphisms from A to B, I will say that F is M2 homotopic to G if iota F is homotopic to iota G. And when I write homotopic, I mean polynomially homotopic, or if you want, A1 homotopic. Okay, so here's the theorem. So I put together results that we had with my former student Montero, which are published, and results from current ongoing work with my current student Santiago Vega. So say E and F are SPI. There is a field. With involution. And that you have psi from cocker ME to cocker MF and isomorphism. Then psi lifts to an M2 homotopy equivalence. LF. So there is a homomorphism from LE to LF and a homomorphism from LF to LE, and both compositions are M2 homotopic to the respective identity maps. If, moreover, C sends 1 to 1, then you may drop the M2. So if C maps 1 to 1, then you can lift it to an actual homotopy. So that both compositions are homotopic to the identity without passing to M2. Yeah. And second thing, with hypothesis on L and involution, which are satisfied, for example, by C with the identity involution, we get the same thing, but with now involution preserving maps. With less hypotheses, for example, for C with complex conjugation, then we get maps from LE to M2 LF and from LF to M2 LE with a certain special evolution, so that both that you can compose this with this by applying M2 to this one, and the compositions are homotopy M2 homotopy equivalent to the respective inclusions. And finally, so these are positive results. So in summarizing, our results say that the answer to the question, what happens with the Leavitt path algebra for the classification question is, the answer is, so if the K0s are the same, then the algebras are the same up to homotopy. So the answer is yes up to homotopy. But here is the following result. Remember, I put this, I introduced this notation of the Leavitt path algebra with a bar, which is with this bar involution. So suppose you take L2 over the complex numbers and the complex numbers with complex conjugation, and you take K0, you take L2 with the bar involution, and then you compute K0H. What is this H above? It's Hermitian K-theory. So we take the involution into account. From here and above, these co-kernels are the K0 groups which do not take the involution into account. This one does. And here, K0, we get C mod 3, which is not 0, as opposed to K0, which is 0. And when we do the same thing with L2 minus, we get C mod 7. So they cannot be isomorphic. These algebras cannot be star isomorphic. Moreover, there cannot be a star algebra homomorphism from here to here, mapping 1 to 1, because otherwise there would be such a map between these two, and there isn't. And because of what I observed before, there cannot be any star homomorphism from L2C to L2C without the bars, to L2 minus C without the bars. That is a star homomorphism, sends 1 to 1, and is C mod 2 homogeneous. There can still be one that is not C mod 2 homogeneous, okay? But at least we have an abstraction to the C mod 2 homogeneous case. So that's the end of my first part.
Okay, thanks. Okay, great. So actually there was a question. Okay.
Yeah. I see in the chat there are questions. What sorts of maps are N2 homotopic but not homotopic? Well, I had to think about it, but in general, when you say there are things that you prove, say when you do some K-theory calculation, sometimes it suffices to use polynomial to prove that the maps involved to prove that they are the same. Sometimes it suffices to prove that they are homotopic. So the only property of K-theory that you use is homotopy invariance, which holds under good circumstances. But sometimes it doesn't suffice with that. You also need to use matricial stability. And that means that you need both. So an example of that is the following. So suppose you have your ring R, and you have an element. You have elements S1, T1, S2, T2, so that Ti Sj is delta Ij, and that that's it. And so you consider the homomorphism from R to R that sends X. So it's phi I. Yeah. So this homomorphism phi I is M2 homotopic to the identity for both I. And so the homomorphism that sends X to X1 X T1 plus S2 X T2, this phi is homotopic to twice the identity. So this is 2 times the identity. This is homotopic to the identity, M2 homotopic, but not in general, not homotopic. So this is relevant because any purely infinite simple ring contains elements which satisfy these relations. So if you have the homotopy classes of maps from a rank A to R, the M2 homotopy classes, then this forms an abelian monoid with this sum. And that therefore, for that you need M2 homotopy, not just homotopy.
Okay.
So we can divide by 2,
Yeah.
so to speak. Yeah, you can add.
So would now be a good time for a break?
Sure.
So so maybe since we're running a little behind schedule, let's do a 20-minute. Let's divide into breakout rooms for 20 minutes.
I don't hear. Now I hear myself. Should I start or I will wait?
Yeah, yes.
Okay. So so now I will talk about Bivariant case theory. So say you start with L, a commutative unital ring with involution. Star. And we assume that such that there exists a lambda in L, so that lambda plus lambda star is 1. So the first example that comes to mind is when 1/2 is in L. So 2 is invertible in L, and then you can take lambda to be 1/2. Since the only involution over the integers is the identity, then this will be self-adjoint, it will be equal to its star, so it satisfies that. Second, so suppose you have any ring, and then without involution, and then you write inv A for A plus A op with involution AB star is BA. Okay, this is an involution, and if A has a 1, then you may take lambda equal to 1, 0, then lambda star is 0, 1, you add them up, you get 1, 1, which is the identity. Okay, so we write alg star or alg L star for the category of L algebras, unital or not, with involution, which is an isomorphism from A to A op, satisfying that if you apply it twice, you get the identity, and satisfying this identity for mu in L and A in A. Okay, so it has an evolution, and the evolution is semi-linear with respect to the ground ring L. Okay, so for example, you can take an algebra over L, which doesn't necessarily come with an involution because you forgot it in the office and I cannot access it. And then you apply this inv, and you get a star algebra over inv L. And this is a category equivalence. The inverse takes maps B to the self-adjoint elements of B, which are all the B's such that B star is B. Okay, so algebras in this just to emphasize that algebras are a particular case of star algebras. Okay, so I will need matrix algebras with and put different involutions in my matrices. So I will write Mn for MnL equipped with the usual conjugate transpose involution. This involution is the adjoint with respect to the canonical inner product, where here this is x star y, or if you want x star identity matrix, and then y. Okay, right, and then I take the union of all the Mn's, and this is M infinity, the finite matrices of arbitrary large size, also equipped with this involution. And then M2 comes with several different involutions. So there's M2 with this involution, and then there's M plus or minus, which is M2 with involution that corresponds to the adjoint operator with respect not to this form, but with respect to this form. Okay? This is the hyperbolic plane, if you will. And then we have M2 plus, which is M2 with involution associated to this form. And since our assumption of this lambda assumption, the assumption that there is a lambda such that lambda plus lambda star is 1, these two are isomorphic. And finally, we have M2 minus, which is M2 with the involution coming from the adjoint with respect to this other form. So all forms so far were symmetric. This bilinear form is anti-symmetric. Okay. So then we write MA for Mn tensor A with the tensor product involution, and then etc. Right? So if we write, say, M2 minus A, that means M2 minus tensor A, and so on. So there are two special maps that I want to consider iota and iota plus, which to be pedagogical, I should write iota infinity to distinguish it from that, but I don't do that. And both are given by the same formula. A is mapped to E11 tensor A. E11 is the matrix, the unit, the matricial unit, and this sends A to the upper left-hand corner. Okay. So this both cases we get star homomorphisms, and then say you have a functor H from star algebras to some category C. Then you say that this map is stable if H of iota and H of iota plus are isomorphisms for every A. Okay, so that's matricial stability. And the next comes excision, and excision is excision with respect to the class of extensions. So what is extension? So an extension is a short exact sequence. This is an A. Where all the guys there are algebras, and all the maps are maps in the category alg star, so they are star homomorphisms. So that this is exact means that this is the kernel of this one, and this one is onto. So this is a quotient map, and this is an isomorphism and onto the ideal. So this is a star isomorphism. So this is, you may think that this is a star, to say the ideal of A, closed under the involution. Okay, so this is an extension, and we say that the extension is semi-split if it splits as a sequence of L modules. So it has a section that is additive and preserves the L module structure, but it's not a ring homomorphism. Okay. So fix either all extensions or the semi-split ones. So we fix a class of extensions, either of these two. Okay, and then suppose you have a functor H from star algebras to T, which is a triangulated category. Then H is excisive, means that to every sequence extension in the class, H associates a triangle which is a triangle in T. It belongs to the distinguished triangles of T. Okay, so that's what excision means.
So sorry, so there's a question. Is semi-split a condition, and is L is a field?
No. If L is a field, the two options are the same.
But you're not assuming that. Okay.
One thing to point out is that because of the lambda assumption, the assumption that there is a lambda such that lambda plus lambda star is 1, any short exact sequence which is semi-split is automatically has a linear splitting which commutes with involution. So over a field which of characteristic 2, you will have a lift, you will have a section, a linear section, but it might not commute with involution. But under the present circumstances, it even commutes with involution if L is a field of characteristic non-2. Okay, so yeah. So here is a theorem. So I put together here. So with Andreas Tom, we did the non-Hermitian case, and now with Santiago Vega, we did the Hermitian case, but the idea is the same. So there exists a functor, JH from Alg star to KKH. So KKH is part of the thing that exists. So there exists a triangulated category KKH and a functor JH, which is homotopy invariant, stable, excisive. This depends on which class you fix, right? But fix one of them, is excisive with respect to that class of extensions, and is universal initial with those properties. Okay, moreover, in this category, if you take home in KKH of JH of L, JH of A, and you loop it, so I use homological notation. So for me, N means N loops, N-fold loops. Then this is as if we were in need of H's. There are two here. So this is homotopy Hermitian K-theory. So is Karoubi's Hermitian K-theory made homotopy invariant. So it's the same idea as Chuck's Weibel's homotopy algebraic K-theory. Okay, so let me introduce some notation. So I will write K, K, N, H, A, B for home in KK of JHA and JHB looped n times. Let me erase this here. Okay, and yeah, and then KKAB is just KK0 of AB. So these are the Bivariant Hermitian K-theory K groups, Hermitian K-theory groups. They depend on the two variables. They are covariant on the first and contravariant on the first variable and covariant on the second. and they satisfy excision on both variables. Okay, so an example. Remember, we have a category equivalence between algebras over the ring L and star algebras over the ring IMB. So this leads to an equivalence between KK and KKH, KK over L and KKH over IMB L. So what is this KKL? So it's the target of the universal homotopy invariant, matricially stable, and excisive functor that is universal. And this we constructed with Andreas Thom in 2000. The paper appeared in 2006. And what this tells you is that you recover it as a particular case of this hermitian version. And in fact, if you take home of L here on the left and A on the right, you get homotopy algebraic A theory, and that is also contained in this because when you do KHH of IMB A, then this is the same as KH of A. Okay, so it strictly contains the non-Hermitian case. Now, now suppose, and this here you do not need an involution of N, but suppose you do have an involution of N on N. Then you can map L to IMB L by sending a mu to mu star. This is a star homomorphism. Okay? And so you can go from algebras over L to star algebras over IMB L by this IMB functor. And since you have this star homomorphism, every star algebra over IMB L is a star algebra over L. So you land L below and star above. And I will abuse notation and call this composite functor IMB. Okay, so you can go from algebra, so L has an involution, and you can go from algebras over L to star algebras over L. There is a functor in the opposite direction, which I call res, which simply is the forgetful functor. So this is analogous to the situation, the CMOD2 equivariant situation, when you have an induction and a restriction functor. Only that the CMOD2 action is not such because it doesn't go from the ring to the ring, but from the ring to the opposite. Okay, now it is an exercise to, not difficult, to show that the IMB functor, this functor, is right adjoint to the restriction functor. And therefore, the same happens in KK. But moreover, in KK, you also have the opposite. I mean, here IMB is right adjoint of res, but in KK, not only IMB is right adjoint of res, but it is also left adjoint to res. So in KK, in KKH, A inv B is kk of res A B, but we also have kk h of inv B A equal to kk of B res A. So it's bi-adjoint. These two functors are adjoint to each other in both directions. So you get a unit map, a Yoko unit map from the composite. So say lambda is inv composed with res. This goes from alg star to alg star. And now L is always the same, so that's why I don't write it. And in fact, you can show that lambda A is isomorphic to lambda tensor A with the tensor product involution, where lambda is just L plus L with involution lambda mu star is mu star lambda star. Okay. So the adjunction unit is the map going from L to lambda that maps A to AA. So this is a star homomorphism. And the co-unit, so the co-unit is the co-unit for an adjunction in the opposite sense, this one, that does not hold at the level of the algebraic categories, but only in kk. However, the co-unit is induced by an actual homomorphism that, which we call eta, that goes from lambda to M2 plus, and which sends AB to the diagonal matrix AB. So in M2 plus, this M2 plus, under my assumptions, the lambda assumption, this M2 plus is the same as what I call M plus or minus. But in the involution that it has here, the involution does the following. It sticks a star in here and here and changes the order. This is the same it does here. So that's why this is a star homomorphism. Okay. And now you can take the homotopy fiber of phi and the homotopy fiber of eta. So by this I mean the polynomial homotopy fiber. It's some pullback using algebras. Okay, and so the theorem that we have is that JH V is JH M2 minus U of 1. This M2 minus was M2 with this involution coming from this anti-symmetric form. So this says that V is the same as U up to a change of symmetry and loops. So as a corollary, you get Karoubi's fundamental theorem for KH, which says that if you define Bn of A to be KHN of B tensor A, then this is the same as KHN plus 1 of H of U tensor M2 minus A. And this is UN plus 1, change of symmetry A. So this is exactly, if you substitute Quillen's K-theory for this Weibel's homotopy K-theory, you get back Karoubi's fundamental theorem. So it is a version of Karoubi's fundamental theorem for homotopy K-theory, and which is deduced from this one, but this is more, right? It says that the same holds at the Bivariant level. So this is a nice structural property that Bivariant K-theory has, but it's not related to my problem. Okay, so write C of U for C of X modulo X squared minus 1. This is the group algebra of the cyclic group with two elements, the group ring of the cyclic group with two elements. And U, I identify it with the class of X, right? So this is a ring, and it maps to KH0 of L whenever L is a commutative ring that satisfies this lambda assumption. You can map 1 to 1. So what is this 1? This 1 is the 1-by-1 bilinear form, the bilinear form in L, that is the identity. And then you map U to the bilinear form -1. So this maps to KH0H of L. And so since in KKH, in the category KKH, everything is all the homes are modules over this ring. And so they are all modules over CU. Okay, so here's the theorem. Which in the non-linear part we did with Montero, the non-Hermitian part we did with Montero, and the Hermitian part with Vega, that says that there are triangles in KKH as follows. You take JH of L to the E0, ME, JH of L to the E0, and then JH of LE. Okay, so for example, so JH of LE is, remember that its K0 was the co-kernel of this matrix, and now this gives you that it is the cofiber of this map in the triangulated category KKH. So for example, if E is the rose with n petals, the graph with one vertex and n loops, then this is multiplication by 1 minus n, or by n minus 1. And so this triangle, you can, if you are this in the setting where you only allow semi-split exact sequences, as we are allowing here, then you can tensor this with any R, and you still get a triangle. And so this means that this algebra Ln tensoring with Ln is equivalent to taking C mod n minus 1 coefficients in K theory. Okay, so this LE is always the cofiber of this, and in particular case, when you have Ln here, you put n minus 1 here, or y minus n. And the second thing is what happens if you now consider JH. This is with the involution star. But what if you consider it with involution, with a bar involution? Then ME, remember, it was the identity minus the transpose of the incidence matrix. So here you put U times the identity minus the transpose of the incidence matrix, where U is this U. So this is allowable because this is a homomorphism between here and here, because precisely this everything is a modulo over this and therefore over this. Okay. So, for example, when L is the complex numbers equipped with complex conjugation, the whole map here is an isomorphism. And using this is how we get our calculation for K0H of L2 and L2 minus over the complex numbers. Yeah. So, yeah. Okay. So this is useful. So, for example, when C in what follows, I will draw a consequence from this and explain you how it is used for our problem, and then I will stop. Okay. So from now on, we will assume that the canonical map from here to here is an isomorphism, and that KH minus 1L vanishes. So if you assume this, then of course this also holds without the H, and therefore it so you get a long exact sequence of KHs, and if it is immediate from these assumptions that then KH0 of LE is the cokernel or ME. Okay, so if L is a field, then this is true, and KH0 is just the usual K0, and we get what I said before. Okay, so but this holds also when L is the integers, say. So it doesn't hold only for fields. Okay, so using this triangle, the first of these triangles, and using these assumptions, we get a universal coefficient theorem, which goes as follows. So here you have X C of coker ME and KH H1 R. So R, any star algebra. This maps to KK of LE R, and this maps to home coker ME KH 0H over direct sum, and this will be onto direct sum home of ker ME KH1H of R. Okay, so we get that exact sequence for any R in Alge. Okay, and yeah, and when R is LF and L is a field with involution plus assumptions, we get that this is isomorphic to let me put star here. So here this is the homotopy classes of star homomorphisms, so homomorphisms which commute with the involution, which are, the M2 homotopy classes of homomorphisms which preserve the involution, modulo N2 homotopies which also preserve the involution. And this plus means the group completion. And this is actually isomorphic to a certain sub-semigroup. So this is a group. And in fact, it lives inside so it's similar to what happens with K0 of a simple purely infinite ring. So here I am assuming R, Aleph, and E and F simple purely infinite. For this isomorphism. For the above, I don't need to assume anything for the UCT. Right. So if E and F are simply purely infinite, and R is LF, then what happens is that this is just because this is an abelian monoid where the sum is the sum induced by the S1, T1, S2, T2 that I wrote before the break. And so this is an abelian monoid. Inside of it lives so its group completion actually lives inside of it. It's an abelian group, which is embeds as a semigroup here, meaning that the zero element, the neutral element, is not the same, just as it was with K0 of a simply purely infinite ring. And yeah, and so what? So how does one deduce these equivalence results from this? Is, I mean, so suppose you are given an isomorphism between coker of ME and coker of MF. Then ME and MF are square matrices. And so their cokernels modulo torsion, so modulo torsion, if you divide this by modulo torsion, you get the kernel of the same matrix. So if these groups are isomorphic, then the same groups modulo torsion are isomorphic. And okay, and this cokernel, this is vertices, the free abelian group generated by vertices modulo certain relations, and each vertex corresponds to a projective module. You equip that projective module with the form, with the identity, and this gives you a projective module with a bilinear form, and so this maps to here, to KH0 of L F. So if you have this isomorphism, then composed with this canonical map, you get a map from here to here. So you have something here. Similarly, this kernel maps to the kernel of MF tensor with KH0 of L, which, using the triangle I put before, receives a surjection from K1H of LF. Now, but this is the kernel of a matrix, so it lives inside of a free abelian group, and therefore it is projective, and so there is a map here. That map lives here. So you have a map here and a map here, And you need to show that you can lift this to a homomorphism, to the class in KK over a homomorphism. And then you need to show that that homomorphism is an equivalence. And this is what we do. So that's it.
Thank you very much. Let's thank Guillermo first. And I guess let's we can ask questions now. So if anyone has a question, please unmute yourself and ask. So maybe I'll start with a question. So I was just wondering, so when you define this this bivariant category in terms of the category of algebras and a universal property, is it clear from that you have so if you have algebras and a bimodule between them rather than an algebra map, is it clear that gives you a morphism in the bivariant category?
Well, if you have, I mean, if you have a, yeah, well, bimodules, if you have a Morita context, so you need a projectivity on one side, at least, then you have, so one ring embeds as a corner in the other one. So you have, so we need to do unitary rings for that, but I don't think you worry about that. So you get an isomorphism from, or a map from R to EM. So if, say, R is the endomorphisms over S of P, then P plus some Q is S to the N. And then taking E to be the projection onto P, you get an isomorphism from R to matrices over, so this, you can map R to matrices over S, right? So with the Morita context, you have maps not from the ring to the ring, but from the ring to the matrices on the other ring, and that gives you a KK class. Yes, yes, and matrix invariance. So from matrix invariance, you can deduce Morita, that it preserves Morita equivalence class.
Great, thanks.
Can you say a little bit more about the assumption of KH minus 1 equals 0 at the ending here? Where does that come in?
So you want, but this KH is not the Hermitian one, but the usual one. I mean, I wrote, so in forget the H. I mean, one of the H's, the little one, the one that indicates Hermitian. So there was this triangle, right? And so you want to say that K0 of this guy, or KH0 of this guy, is the co-kernel of C to D0, C to D0, and then here the matrix. Then you need one way to assure this is by asking that the next term is 0, that KH minus 1 of L, which will come power to the E0, be 0. And then in order for this isomorphism to work, you will also need to assume that KHH, I mean, you need that you are regular enough so that that you can remove the big H. And here we use the Delice field because we need this. And yeah, and this is 0 because of this, you know, result of Wranitzky if L is a field where 2 is invertible.
Because I had a question. So let's say in the context of Levitt path algebras over a field, is this a situation where homotopy K theory is the same as usual K theory, and where like negative K theory is 0?
Yes. Moreover, you just need that I mean, you can take a Levitt path algebra over any ring, and you need that the ring, say commutative ring, you need that this commutative ring be regular supercoherent. If the commutative ring is regular supercoherent, which means that every finitely generated project, every module has finite homological dimension, finite projective dimension, and that it is coherent, meaning that the category of finitely presented modules is abelian, and that it's supercoherent means that the same is true of all the polynomial rings on any number, finite number of variables. So if this happens, then the Levitt path algebra is K-regular and has trivial negative K theory. So it follows, if 2 is invertible in L at least, that that Hermitian, homotopy Hermitian, and usual Hermitian K theory are the same for the Levitt path algebra.
You see any way?
For example, that means that you're proving this result up to and to homotopy. That sort of it implies that it's as if the original conjecture is true, at least at the level of K theory. I mean, it's just a way to rephrase it. Maybe never mind.
Is that Bert?
It is. Hello. Yeah.
Yeah. Hello. But I didn't catch what.
I think actually it wasn't important. I'm just kind of thinking it through. So maybe I'll let somebody else ask a question.
Okay.
When Karoubi originally did this, he had a version for K1 or KH1. Do you have some sort of a way of interpreting those things? I'm going towards higher K theory, and then I'm going towards spectra.
Well, I mean, for okay, you may ask whether Bivariant K theory, the Bivariant K theory groups are the homotopy groups of some functorial spectrum, and the answer is yes. This was worked out by a former student of mine, Rodriguez Cirone. I suppose that the same should go through in the Hermitian case, but we haven't worked it out. And in particular, we haven't considered whether you get a map of spectra or anything, but it should work. I mean, what we do, we use Karoubi's element to do this cap product, which induces the equivalence between V and U, the loop, and loops of U. But you can do this with an element. You do not need the spectrum.
Are there any more questions? If not, let's thank Guillermo again.
Thank you.
Thank you. Bye.
And we'll meet again in 2 weeks.
Okay.
Bernard Cyril. Yep. Thank you. Bye-bye.
Yeah, thank you for the nice talk.
Thanks.